Wanted to work through a problem that involves a lens and the image of an object in the lens. We're going to calculate the location of the image and the magnification of the image and whether the image is upright and inverted. So in this particular problem, I'm told that the Queen of England has placed a gold coin, one of her many gold coins, in front of a lens. We're told that the coin is 20 centimeters from the lens, so that's the object distance. We're told the lens has a focal length of minus 32 centimeters. That actually means it's a diverging lens. And the question is, figure the location of the image, figure the magnification of the image. And we're actually also going to sketch the formation of the image. And maybe what I'll do first is ray trace, make the sketch of the image formation, and then we'll do the calculation of the image formation. It's handy to do the sketch and the calculation as one checks the other. The sketch can check the calculation, and also the calculation can check the sketch. So starting with the sketch, here's an optical axis. And on this axis, I'm going to place the Queen's diverging lens here. And I'm going to mark the focal length. So this is the focal length or focal point. And then I'm going to sketch the location of the object and start drawing some rays that are from the object that are incident on the lens and refracted by the lens, and we'll construct the location of the image. So there's several rays we can draw. A personal favorite of mine for the lens is the one that goes straight through the center of the lens because it's undeflected. It's easy to draw that one. A second ray is one that heads straight towards the lens, parallel to the optical axis, and then is refracted for this diverging lens such that it appears to come from the focal point, the focal length. So that's this ray in magenta here. And from those two rays, we could construct the image. Let me just draw one more ray. To draw this one additional ray, I'm just going to mark the focal length on the other side of the diverging lens. So this ray is the partner to the magenta ray. It actually heads towards the focal point on the far side of the lens, something like this, and then is refracted to be parallel to the optical axis. And so you notice that both these rays, the magenta one and the blue one, are bent away from the optical axis. That's what diverging lenses do. So now we can imagine that our eye is over here, and our eye collects these rays, and our eye and brain reconstruct the point that these rays are coming from, the common point that they're coming from. So something like this. Here's the image. And so we've constructed the location of the image from the location of the object by drawing a few rays that obey the laws of refraction when the light is double refracted at the lens. And so we've got an image that is roughly half the size of the original object, the gold coin. We got an image that's upright, and we got an image that will be virtual. The light rays aren't actually coming from this location. They just appear to come from that location. So now let's go ahead and we'll do the calculation. And there's two things to calculate here. The first part is the position, the image position. Then the second part will be the magnification. For the position, we're going to use the lens equation. And if you remember, the lens equation relates the object and image distances to the focal length of the lens, that sort of personality, character of the lens. In our case, we want to rearrange this equation for the image distance. That's the unknown. So it's the difference between the inverses of the focal length and the object distance. We can rearrange this equation to make it handier to use for us by identifying a common denominator here. So FP would be a common denominator. And so rewriting the difference of the two fractions in terms of a common denominator, we got P minus F in the numerator, we got PF, the common denominator, in the denominator. And then we can take the inverses of the far left and the far right to get an equation for Q. Q, the image distance, will be PF over P minus F. Then I can just start filling in the numbers. So the object position was 20 centimeters. I'm going to be naughty here and not put in the units because I'm running out of room. The focal length was 32 centimeters, minus 32 centimeters. I'm putting that in. Careful with the sign. And then in the denominator, I've got 20 centimeters minus 32 centimeters. So this is actually 52 centimeters. And if I go ahead and calculate this quantity, which has units of centimeters, because there's centimeters squared in the numerator and centimeters in the denominator, I get, it's going to be negative, minus 12 centimeters. Actually, minus 12.3 centimeters, but I didn't have room for the 0.3. So that is the location of the image. And it says that the image is on the front side of the lens, which is where our image sketch has the image. So that makes sense. And its location from the lens is about 12 centimeters, which is roughly half, a little over half, the object's location for the lens. And that makes sense with our sketch. So it's a good confirmation that a sketch is approximately right, or it's a good confirmation that a calculation is right, as they're consistent with one another. Now we just need the magnification. That's easy now. Magnification equation says that the magnification is the ratio of the negative of the image distance to the object distance. And we know both of these quantities now. So we just got to fill in minus 12.3 centimeters divided by the positive 20 centimeters. And we got two minus signs, so we're going to get a plus. And the numerical value here is 0.61. And so this magnification equation is telling us that our image is smaller. It's 61% the size of the object, which looks about right on the drawing, and that it's upright, which corresponds to the image on the drawing. So again, we've confirmed the drawing or confirmed the calculation. Anyway, that was just an example of working with lenses to figure out the image of an object, the properties of an image in an object. This was a converging lens. This was a diverging lens, and diverging lenses bend the light away from the optical axis, and you can see that in the sketch. And diverging lenses actually always make virtual images, and this was a virtual image. It was located on the front side of the lens. There are no refracted rays on the front side of the lens, and so it must be virtual. We just think the light is coming from that location. The light is apparently coming from that location. It's not truly coming from that location.